Okay, so we want to talk about rationalizing the denominator. This is just another skill that comes up pretty often where we have to deal with radicals. And the name refers to rationalizing. A rational number is one that you can write as a fraction or a decimal that ends. Okay? Famous numbers that are not rational or irrational would be like weird numbers like pi and e, but more commonly square roots. Right? You can't write the square root of 2 as a fraction, where it's like a whole number over a whole number. I mean, you could write the square root of 2 over 1, but that's not what we're talking about, that rational form. So to rationalize the denominator means that you're going to have a radical in the denominator, right? You want to get rid of it. So just a quick example here. Suppose we have the square root of 2/3. And kind of a general rule in here when it comes to rationalizing the denominator, if we ever see a variable in the denominator, maybe there's like a square root of x, I'm fine if you leave that there. It's fine if it has variables in it, but if you do just have a number under the square root, you do want to go ahead and rationalize it. You see the difference there? Is that good? All right. So what we're going to do here is we talked about yesterday, that we know that if you have a single square root and there's a fraction underneath it, we can express that as the square root of 2 divided by the square root of 3. Okay. Now the square root of 2 is irrational, but it's in the numerator, so it's fine. Okay, we want to get rid of this square root of 3 in the denominator. And the way we do that is we're going to take advantage of the property that said, if you have the square root of u, or the nth root of u to the nth power, that we're just going to get u, correct? That's what we're looking to use here. So right now, we have the square root of 3. What we want is the square root of 3 squared. Okay, because the squared and the square root will cancel. We know that whenever we have a fraction, if you multiply the numerator by a number, you also must multiply the denominator. Well, or vice versa, the denominator and numerator. So we'll take the square root of 2 over 3 times the square root of 3 over 3. Okay, and then this is a case where we're working with what's called an expression. There's no equal sign on our page. So I would avoid trying to write equal signs if you go from step to step. If you'd like to work sideways, I would just use arrows. It tells you the same thing, but it's not bad notation. But this is an expression. Really, the only way that we can change an expression is you can add 0 to it, or you can multiply it by 1. Sometimes when you add 0, you do something like add 4 and subtract 4. Or in multiplying by 1, you do these fancy forms of 1, where it's radical 3 over radical 3, which is actually equivalent to 1. So as we multiply this now, we'll get the square root of 6 on top. And then on bottom, we get the square root of 3 times the square root of 3. Now, I wouldn't bother writing the square root of 9, because that's not what we want. We want to see this as the square root of 3 squared. And probably I wouldn't write that step either. But we know the square root of 3 squared is just 3. So we'll get radical 6 over 3. Now we're done. That's our final answer. I still checked, though, and made sure that radical 6 didn't simplify. So I thought about my perfect squares. 4 doesn't go into it. 9 is too big. So there we go. All right. Any questions there? And they're really straightforward with square roots. Right? And when we do trigonometry a lot, we'll have these different ratios that we tend to simplify. Here's 1 over the 4th root of x. So a similar type of problem. If you want to here, go ahead and try that one. And then let's go ahead and try the 5th root, and we'll go over these together, of x squared over y cubed. That's not a very good 5. Okay, so if you want to, just try those, and we'll come back together and look at those. All right, let's go ahead and take a look at these. Now, a little different here is we have a 4th root. Okay, so kind of going back to this idea here, we're going to need to get the 4th root of x to the 4th. Okay, so we're missing actually 3, x cubed underneath that. So with this one, we just take what we have, and we'll do the 4th root of x cubed over the 4th root of x cubed. Okay, when we multiply that, that gives us the 4th root of x cubed over the 4th root of x to the 4th. And we all know the 4th root of x to the 4th is just x, correct? Oh, is that 2? Okay, so I noticed that I need to get a fourth root of a fourth power to get it rationalized, because then it'll just be a plain old x on bottom. So what I did is I said, well, I have 1 underneath the fourth root. I need to get 3 more. So multiply the top and the bottom, right, by a fancy form of 1. That's all that is. And then here we get the fourth root of x to the cube of x cubed, and then this would be x times x cubed to be x to the fourth. So the fourth root of x to the fourth would just be x, and the fourth root of x cubed over x. Now up top, you can't really simplify any, right? I mean, there are other ways you could write that expression. There are actually a bunch of other ways, but this is going to work for us for now. We good there? Hopefully you guys tried that and were successful. Here we have a fifth root of x squared over y cubed. Looks a little bit more involved. Similar to how we started in the first example here, we'd like to go ahead and just think of it. I like to think of it as just a radical over radical. You can skip that step if you are comfortable doing that, but if you ever have to ask yourself if you're comfortable skipping a step, you're probably not. You should probably go ahead and show it. If it's, you'll know if you're able to. So in this case, now the numerator here has stuff under a fifth root, and it's going to have stuff at the end under a fifth root. We don't really care what's in the numerator. All we care about is we have to fix this denominator. That's it. So to fix the denominator, we need to get the fifth root of y to the fifth. Right? So we know that when you multiply a base times the same base, you add the exponents. So we're going to need to multiply by y squared, fifth root y squared on top and bottom. So we'll get the fifth root of x squared, fifth root of y cubed, fifth root of y squared over fifth root of y squared. And again, I'm probably showing more work here than I might actually do on my own, but usually more work is not a problem. So with this, as we work through this then, for the numerator, we have the fifth root of x squared, y squared. On bottom, we have the fifth root of y to the fifth, which is what we wanted, right? That's a fifth root of y to the fifth. We can get rid of that, and the fifth root of x squared, y squared over y would be our answer there. So all three of those, we went ahead and rationalized the denominator. The denominators of our final answers are y, which we assume is a rational number, right? And then x, which is a rational number, and then 3, which we know is a rational number. Again, the one thing I did mention is as we work through the year, we don't always have to rationalize when they have radicals in the bottom. Now, for practicing this, we will, but that's a case where a lot of times you can leave those answers and it's okay, because it gets really clunky to try to rationalize them all the time. Okay, so we're going to start quickly talking here about rational exponents, but before that, it would be a good idea to just review our exponent rules, like how we deal with exponents. Okay, if you don't remember, radicals and exponents are basically two sides of the same coin, right? It's just two ways of expressing the same types of things. Shouldn't be any surprises here. Let u and v be real numbers, variables or expressions, and let m and n be rational numbers. A lot of times when you're defining these, they say integers, but they actually works for rational numbers too, meaning fractions. All bases are non-zero. Bases are 0, you kind of got a mess. But here, if you have a base times the same base, you add the exponents. So an example of that. Does that make sense to everybody? We'll look at these. If you have a base divided by the same base, you subtract the exponents. Okay. Now notice here there's no addition or subtraction going on over here. If there is, it kind of throws a wrench in the works, so we want to watch for that. Any non-zero base to the 0 power is always 1. That's a definition that's really kind of important theoretically in math, so make sure that you're just aware of that. It's usually one of the easiest questions you ever have to answer, but if you don't know the answer, it can be tricky. This is a nice one here. I'm going to add a little bit to it. U to the negative n power. If you have a negative exponent, you can move the base to the denominator if it was in the numerator. If it's a negative power in the denominator, you can move it to the numerator. It's to move things around. I also like to think of it maybe in terms of, say if you have maybe u over v to the negative n power, so you have like a fraction to the negative n power, it'll just become v to the nth over u to the n. So they just switch, right? So I always just think to get rid of a negative exponent, you move the base. If it was in the numerator, now it moves to the denominator, and if it was in the denominator, you move it up to the numerator. Now again, if there's addition or subtraction going on in the numerator and denominator, it doesn't work. Right? Addition and subtraction makes things harder in algebra, which always seems a little problematic to me, but it tends to. Here, this was called the product of powers, and this is the power of products, which doesn't really matter at all. But this just says if we have two things multiplied together, raised to an exponent, that you could just raise each piece individually to an exponent. So a very simple example would be if you had, say, 3x squared cubed. Maybe you get something like that. So what that's telling us is we could take 3 cubed, then we could take x squared cubed, and then 3 cubed is 27. Here is a case, it's the next rule, right? If you have a power to another power, you multiply them, and then you would get x to the 6th. So that's an example of that. And then here, this was an example of this property right here, which says if we have a base to a power raised to another power, you multiply the exponents. And lastly, if you have a quotient to a power, you could just as easily take the power of each of the numerator and the denominator. Do it that way. All right. So next thing we want to talk about is rational exponents. Okay. Again, they're going to serve the same purpose as radicals. Sometimes these are so much easier to work with. Other times radicals are so much easier to work with. I know as a calculus teacher that rational exponents are a ton easier than dealing even with like a square root. Like it's much easier to deal with a 1/2 power than it is to deal with a square root. Like, so it's well worth knowing both ways. So just sort of our definition here, and this hopefully is not new to you, but it might be written out differently. Let u be a real number variable or algebraic expression. So it could be something like x plus y or y plus 3, like something with algebra. Let n be an integer greater than 1. Again, because that's going to be our index of our roots. We take the index and get 2 or 3 or 4 or 5. We don't have fractional roots that I'm aware of. We don't do that. Okay, so then if you have u to the 1, the nth root of u, which we're used to seeing from earlier today and from yesterday, is the same as u to the 1 over n power. Okay, now, we just talked about exponent rules and we talked about negative exponents. This is not negative, this is just a fraction. Okay, so be careful, that's a different rule that said you could flip the base. So if you see a 1 over n power, it means you're taking a square root. Graphing stuff in your calculator, if you have to graph the 4th root of x, a lot of times I'll just put x raised to the 1/4 power. They're equivalent. When it gets more interesting is when we also have this m here. So we have this is 1 over n is a rational number. It's kind of simplified, right, with 1 in the numerator. But a lot of times you have 2/3 or 4/5 or 7/2, so whatever. With that, just remember that the numerator is going to indicate the power. The denominator is going to indicate the root. Okay? So numerator is the power, denominator is the root. And what this piece here is telling us is that, and we mentioned this yesterday, I think we talked about, I think it was like, what was it? I don't know, the 4th root of 16 to the 3rd power or something. Sometimes it's easier to root first and then power later or things like that. You could either write it as u to the 1 over n power, which takes care of the root, then raised to the m power, which takes care of the power. It could look like this in terms of rational exponents. It would look like this if you used a radical symbol, right, in the root instead. or if you can also do the power first and do the root second. So you got a power, you've got a root, right? Power's from the numerator, root index is from the denominator. It's up to you which ones you do first. Usually if you're able to do the root first, if you're able to calculate it, it tends to be easier to do just because it's smaller numbers. Really, it'll improve your math skills if you really try to look for times when you're able to do things by hand rather than grab your calculator. Now, sometimes you got to use your calculator. Absolutely, that's why we have them. But the more you can kind of think your way, how could I avoid having to get a calculator out? So for our example here, we just want to convert some of these. Right? So they're in one form. We want to convert them to the other. A lot of times, so here, obviously, these have radicals in them. These two, we're going to convert those into rational exponents instead. Here we have rational exponents we're going to convert into radicals. There's not always one best answer. There might be different forms that you just kind of have to get a feel for it. So sometimes even checking these, your answer might look a little different, but it's not necessarily wrong. But the more you do these, you start to find forms that are easier to do what you're looking to do. You know, maybe they make it easier for you to do the next step. Because all this stuff, yeah, this isn't from the appendix of the book, it's review before we kind of get into the meat of the course. These are just skills that are going to come up. So we want to make sure that we, you know, that we know them. All right, so here we have the square root of x plus y cubed. Kind of note from earlier from our exponent rules, you're not allowed to say x cubed plus y cubed. That's incorrect because of the plus sign. Right? If there's addition or subtraction, it pretty much stops all of those exponent rules that we looked at. You'll notice none of those had addition or subtraction other than just adding an exponent. So what we can do though is the square root is the same as a 1/2 power, correct? So kind of working through this, and I'm going to use arrows because again, I try to avoid equal signs unless we're actually working with an equation. But here we could write this as x plus y cubed raised to the 1/2 power.
Staff, excuse me for the interruption.
So here we have this x plus y cubed raised to the 1/2 power. To finish this up, we'd want to go ahead and multiply the exponents here, right? That was where you have a power to another power. So that would be, the argument is still x plus y, right? That's an algebraic expression. And now it's going to be to the 3/2 power, would be our most simplified way. That's it. You're not allowed to bring the 3/2 power in there. That's not something that we can do. Questions there? Okay. Yeah, so that's an example there. And again, just wanted to be careful about it. The addition subtraction, we really have to be careful. It's something that we'll talk about throughout the whole semester, throughout the whole year. Okay, so here we have 3x times the 5th root of x squared. All right, a lot going on there. 3x is pretty okay as things look now, but here, instead of doing a 5th root, we could raise that to a 1/5 power. So what we'll do there is 3x x squared to the 1/5 power. And then from here, we'll go ahead and multiply those exponents. So now we'll get 3x times x to the 2/5 power, right? Because 2 times 1/5 is 2/5. Don't put 0.4. This is rational exponents, not decimal exponents. That's not really a thing. Pretty much if you get a decimal exponent, you rewrite it as a rational number and go from there. And then here, we actually do have the same bases multiplied together. Right? If we go back and look at our exponent properties, we can see that if you have a base times the same base, you do go ahead and add those. Right? So here, even though it's just an x, it's actually to the 1st power. So this will become 3. Now the 3 is just a 3, right? It has no power. It's 3 to the 1st. It's just doing its thing. It's hanging out. It gets to be part of the problem, but it doesn't ever really do anything. It just sits there. And this will be x, and then 1 plus 2/5. Okay, we're going to have to write that as an improper fraction. So we know that 1 is 5/5. And I hope you're thinking, oh my gosh, Mr. Mivers, you don't need to show me this. I am so good at fractions that is like a dream problem for me. And I hope that's the case. But you add those up, you get 7/5, so we get 3x to the 7/5 would be our answer there. Now, why this is a really important idea to get comfortable with is if you're doing a problem, something unrelated to this, right? You're doing some problem and you get an answer, and you have this on your paper, and then you go to look at the answers in the back of the book and it has this. If you don't know this skill, there's no way you're going to make the connection between there. You're going to be like, oh, the 3 was right, and then you're going to just be like, everything else was wrong, but it actually was correct. It's just a different form. Especially with textbooks, sometimes too, if you, and not that we use a book much, but you might in the future, but a lot of times the person that writes the text part of the book doesn't write the answers. It's a teaching assistant or a grad student that writes the answers, so they might do it completely different, and their notation might be completely different. So just to be aware of that. So this, again, both of these, A and B, we're converting from radicals into rationals, and how we can do that. The next one here, for C, we got a couple different options here, kind of how you want to do this. What I would tend to do here is notice they're both over 3. They're both one, it's 2/3 and 1/3, correct? So probably our quickest way here would be to say x squared y to the 1/3 power. It's almost like you're using the property, we're using our property here that we had if you have we're kind of going this way, right? If you have u to the m and v to the m, you can write it as u times v to the m, is what we're doing there. And then we know that a 1/3 power is a cube root, so the cube root of x squared y would be, I think, a very acceptable answer there. Now, just to compare, it is possible, though, if you did them each individually, you could get like, it would give you the same answer, probably an extra step, but you could have x squared to the 1/3 times y to the 1/3, right? And then from there you could get x squared y to the 1/3, or maybe, well here, maybe you don't do it that way, maybe you say, well, that's the cube root of x squared times the cube root of y. Then you say, hey, I got a couple of cube roots, right? I could go ahead and put them together, and that'll give you the cube root of x squared y. So however you do that, it works. Last up here is z to the -3/2. So if we think back to our exponent rules, we know that a negative exponent, we take the reciprocal of the base. It's normally the first thing that I do is I get rid of that thing because they just tend to cause problems. So I would recommend your first step here would be to write this as 1/z to the 3/2. Right? So just the base moves. The base went from numerator to denominator. The exponent changed from negative to positive. But notice it's still 3/2 and it's still 3/2. Okay, because sometimes people want to like switch everything out just because it's so exciting. We get that a lot in algebra. Okay, but because of the excitement. But now here as we look at this, the 3 is going to be the power, correct? And the 2 is going to be the index of the root. That's just an old square root. So here we can say 1 over the square root of z cubed, which is decent. That we did say it's okay to leave radicals in the denominator usually. So this is acceptable, I would think. Now, do you notice that if this was a second or square root, right, and this is a 3rd power, we could actually break it up. If you think back to what we did before, and you could have z times the square root of z. Right? And again, what I did there is I wrote this as z squared times z. So the square root of z squared got to move. Is everybody okay with that? Something we've been looking at again, because this is the same as the square root of z squared times the square root of z. That'll kind of take you to there. This is pretty good also. If you did want to rationalize it, we multiply the top and the bottom by the square root of z. And that's going to give us, let's use an arrow. The square root of z. Well, what's radical z times radical z? Z, and then what's z times z? Z squared. So you could also write it like that. But to be honest with you, you just want to be able to, but this is a really good answer. This is a pretty good answer too. And that's not bad at all. Like those are all pretty reasonable. Kind of just depends what you're looking for and what you're doing. Right? So it's okay to just do a little bit extra and kind of see what's going on there. All right. So let's take a look at these. And again, there could be different ways to work through it, different ways to get your answer. You could probably give your answer using radicals, or you could give it using rationals, exponents. It just sort of depends. They're both valid. So let's take a look here at this first one. X squared y to the 9th raised to the 1/3 power. So I know this power is going to come inside on each of those terms, or each of those factors. It's actually just one term for each of those factors. And then here is just an y squared, which will get multiplied in later. So here, you're going to take x squared and raise it to the 1/3 power, y to the 9th and raise it to the 1/3 power. And this is just times x times y squared, correct? Didn't do anything different there. So here, if you take x squared to the 1/3 power, well, 2 times 1/3 is just 2/3, right? Multiply fractions, right? 2 over 1 times 1 over 3 is 2/3. So 2/3. 9 times 1/3 is just 3 times x times y squared. So now at this point, we want to look at the bases, and we want to look for matching bases, and we want to add their exponents. Now, do be careful here. This is actually x to the 1st power. So if you're going to add a 1 and a 2/3, you need to get a common denominator. Okay, so that would mean, let's write this as x to the 2/3 times x to the 3/3, right, because I just got a common denominator there to help my addition. And then y cubed times y squared. Okay, so here we have a base times the same base. We add the exponents. 2/3 plus 3/3 is 5/3. And then y to the 5th. I would probably leave it like that. If for some reason you did have to convert it and make it into a radical, which could be a need for that, you could say x to the 5th cube rooted, and I would put y to the 5th out in front. I always like to put the stuff that's not under the radical to the left of it, because then if your pencil doesn't make the radical very big, you know what's underneath, you know what's not underneath. By making years and years of mistakes in algebra, in pre-calc and calc and different math, I've learned ways to help me write things that keep me from making as big of mistakes. Okay. Or you could even, if you wanted to take a packet of those 3's out of there, you could say y to the 5th, xy to the 5th times the cube root of x squared. That would also be fine. Those are all equivalent forms of the same answer. See, they can look quite a bit different, right? They're all purple at least, though, so whoever it's worth, that helps. All right, this looks like a mess right here. I'm not really loving the look of this one, but let's see what we can do. The first thing I'd realize is that it's nice that everything's being multiplied and divided. We're not going to have any addition or subtraction, which are going to kind of goof us up here. So the first thing I don't like to see is this -1/2 power. So I'm going to go ahead and rewrite it. I'm going to leave this the same. I'm going to leave the 2 up here because the 2 is not hit by the negative exponent, and then move that x down here to the bottom would be my first step. Again, there are lots of ways to get there, right, but I'm going to choose to do that. To me, that looks reasonable. Now at this point, it's just a product, correct? We're multiplying 2 fractions together. So here 3 times 2 is 6, and then x to the 2/3. On bottom, we're going to have to do some work with our exponents here, but we have x to the 1/2 y to the 1/2, y to the 2/5. So we get to have a little bit of fun with fractions here, right? So at this point, we know the 6 is going to be in the numerator. Right? So we've dealt with that. We have to deal with the number part, which is the 6, it's done. We have to deal with the x's. So if you have x to the 2/3 over x to the 1/2, and it might even be helpful to kind of pull that off to the side, that means we're going to subtract the exponents. Right? So 2/3 minus 1/2. We should absolutely be able to do this by hand. That's going to be, we're going to get a common denominator, so 4/6 minus 3/6, which will be 1/6. Now when you're doing that, because for this format where you take a base divided by a base and you subtract them, if it's going to end up in the numerator. Like, thankfully it's positive. If it's negative, it'll still be in the numerator, but if you want to move it down, it'll be negative. There's one way to do that. So let's say we said the 6 is on top, and then x to the 1/6. Now on bottom, we have y to the 1/2 times y to the 2/5. So again, we're going to want to get a common denominator, which would be 10. So y to the 5/10 times y to the 4/10. And then we know we're going to add those. So that's going to give us y, oh, that's a g, that's just wrong. Y to the 9/10. And that's going to be on bottom because both of the pieces that we started with were on bottom. I mean, you could write that using radicals, but it's going to look pretty bizarre. I don't know what would be much benefit, but you could say 6 times the 6th root of x over the 10th root of y to the 9th. I guess you could even rationalize it if you really wanted to. Again, it's not really necessary, but because you have 9 of these, you just would need 10, correct? You need one more. Oh, that's pretty, it would look terrible. I wouldn't do this, but the 6th root of x times the 10th root of y over y if you did happen to do that. But you're good stopping here. Kind of make sure this should make sense, right? That's not too tricky. I rationalized it, and it just looks bizarre and awful, so probably not a great thing.